So this is the beginning of the overview of the 50 multiple choice questions. Before I get into the actual test, I'm going to do a quick review of quantum numbers. So we know that we have N, L, M, and S. Oops. So there's a little delay for you. Sorry about that. So N, L, M, and S. We know that if N equals 1, I'm going to write up here what they are. So N can be from 1 to infinity. L can be from 0 to N minus 1. M can be from negative L to positive L. S can either be a positive 1/2, which means spinning clockwise, or a negative 1/2, which means spinning counterclockwise. So N equals 1, L can only equal 0 then. And if L equals 0, M has to equal 0, and S will either be positive 1/2 or negative 1/2. So for the two electrons that are potentially in the first energy level, one of them will spin clockwise and one will spin counterclockwise, and they'll have to be in the same orbital. Now in the second energy level, L can have two different values, 0 and 1. So M would have to equal 0 for L equals 0, but if L equals 1, then M could be negative 1, 0, or 1. So there would be three values of M, which is why there are three orbitals in the L equals 1 sublevel. And then your positive 1/2 and negative 1/2 would be multiplied by 3 because there'd be three orbitals. Now I'm going to quit putting the spins in because it's hard to write them, but know that there will be 2 electrons per orbital. One spins clockwise, one spins counterclockwise, and they go into the orbitals singularly before they begin to pair up. So they have to make sure that every orbital has one electron before they begin to pair. All right, so now in the third energy level, N equals 3, L could equal 0 or 1 or 2 because it goes to N minus 1. And if L equals 0, M equals 0. If L equals 1, then M equals negative 1, 0, or 1. If L equals 2, it's negative 2, negative 1, 0, 1, and 2. So there are 5 orbitals for L equals 2. If N equals 4, then 0, 1, 2, 3. All right, if L equals 0, then M equals 0. If L equals 1, then it's negative 1, 0, and 1. You seeing any pattern? Negative 2, negative 1, 0, 1, and 2. Negative 3, negative 2, negative 1, 0, 1, 2, 3. So in an F sublevel, or the L equals 3 value, there'd be 7 orbitals. All right, so the letter names, S. All the L equals 0s are called S. L equals 1 is P. S, P. L equals 2 is D. S, P, D. L equals 3 is F. There's a little overview of quantum numbers. So now let's go back to the questions on the test. Number 1, what is the number of sublevels in the second principal energy level? Well, here's the second principal energy level. There are 2 L values, so there are 2 sublevels. So the answer is 2. Number 2, if an atom containing 16 electrons lost an electron, its charge would be. All right, if it has 16 electrons, and it's not an ion, it's an atom, it also had 16 protons, so they're even. So if you take away one of the negatives, now you've got 16 protons still, but only 15 negatives, so the charge is positive 1. So that'd be A. The highest energy level in chromium. All right, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. So 3d is the last place you put electrons in, so that would be your answer. The highest energy level would be 3d. Number 4, the outer shell of arsenic. To show you that one, I'm going to pull in something real fast from. I linked this on your homework page. I'm going to pull this in so you can see it. All right, we're at arsenic. So we want to know which of the following sublevels in the outer shell of arsenic. So we'll pull this in. Here's arsenic. Do that. We'll click on electron configuration, close this down. Okay, so here's arsenic's configuration showing all the orbitals and all the arrows that are representing electrons. So each arrow is an electron. Arsenic has 4s2, a 3d10, a 4p3. So the outer shell would be 4s and 4p. So then you go back to your quiz, and the answer is, looks like 4s, because there was no 4p wasn't listed, so that would be C. All right, an atom when excited can emit energy only in the form of definite quantities. Okay, so it emits energy when it's excited in definite quantities. I'm going to try and quickly pull up something here to show you related to that. It may take me a second to pull it up. I should see Safari popping up here. And I do, but it's on my other screen. So I'm not going to pause the video long enough to really take time to do that. I'll come back to it in a minute. It's running hopefully in the background there, opening up. Okay, the principal quantum number. The principal quantum number, of course, would be the quantum number N tells us the most about the distance from the nucleus. So that'd be number 6 here. Okay, number 7, the quantum number that designates spin, we went through that a minute ago over here. It was the positive 1/2, negative 1/2 quantum number. So you write over here, positive 1/2 or negative 1/2. So that would be D. Okay, the number of values of the azimuthal quantum number determines the azimuthal quantum number is L. And so we look over here, the number of values of L gave us a number of sublevels. So if L had 2 values, there are 2 sublevels. L had 3 values, there are 3 sublevels. So that would be the number of sublevel C. All right, when the secondary quantum number L is 3, so if L equaled 3, the magnetic quantum number M could be all these values, negative 3 to positive 3, so that'd be B. Okay, here's my little animation going back to number 5. I'll let it open up while I'm working here. Number of electrons that can occupy a p sublevel. P sublevel, remember, is L equals 1, so negative 1, 0, and 1. Each one of these orbitals can contain 2 electrons, so the number of electrons would be 2. Okay, so the number of electrons occupy the p sublevel is 6. So that would be B. Which of the following sublevels has the shortest wavelength? Well, the shortest wavelength should be the highest energy. Remember, if a wave is going, it took a lot more energy to make this wave than it did this wave. So the shorter wavelength's higher energy. So higher energy would be 5s. All right, that was the bell for my A3 class. So I'm going to go back to number 5. An atom, when excited, can emit energy only in the form of. Now here's the emission of the energy I'm talking about. So we're going to turn a light on. These are photons of light energy. The photons of light energy are going to slam into this electron. Not that one, that was the wrong one. It's going to slam into this electron. See that little blue dot in the middle? So when the blue dot gets excited and moves away from the nucleus, like it is right here, when it comes back down, it gives off a certain quantity of energy. See it flying off here? But it has to give off that particular quantity of energy. It can't, it's only certain amounts. All the energy changes between these energy levels are limited to specific quantities of energy. We say that energy is quantized. And the energy that's given, that one flying across there, is represented by the equation energy is equal to h times frequency, or Planck's constant times frequency, or we called it E equals h nu. All right, so back to number 5, the answer then, energy can emit energy only in an amount of definite quantities, and that was B. All right, we'll pick up later. That was 1 through 11.